Hello everyone, my name is Avkash, and in this video I am going to show you how to perform machine learning using Keras deep learning library. We are going to perform our machine learning experiment at Google Colab runtime environment. The Jupyter notebooks we will be using in this tutorial are hosted at my GitHub account and they are connected with Google Colab. For this tutorial, I have two separate Jupyter notebooks. In this tutorial, we are going to use a very familiar and publicly available heart disease dataset. Our objective is to learn various deep learning functionalities available in Keras. We will perform EDA. This tutorial is quite different than many others available on YouTube. In this tutorial, we are going to start with the data import. Then we will be performing the exploratory data analysis. Then after, we are going to transform our data. Then our data will be ready for machine learning. After that, we are going to split our data set to extract the training and the target data. For the training data set, we have two separate exercises. In one, where we are only going to use the training and test data, and in the another exercise we are going to use the training and validation data for the training, and then we are going to use the test data. One very creative part of this tutorial is to visualize the real-time loss and accuracy metrics. You are going to write a Python function to get the real-time loss and accuracy metrics values as your machine learning or deep learning training progresses every epochs. It means after every epoch, you are going to get your loss metrics value and your accuracy value. And we are going to plot these two values after every epoch, and everything going to be available in real time. So these metrics will be rendered when we have only training data, and in the second notebook when we are using training along with our validation data. So you are going to see these metrics with loss metrics and validation loss along with accuracy metrics and validation accuracy metrics. At last, we are going to use the model history object where this model training results are stored, and we are going to plot the accuracy and the loss metrics. So this tutorial is packed with lots of information. This tutorial has two Jupyter notebooks, and these two Jupyter notebooks are ready to execute in your Google Colab. So after you clone this tutorial repo and get those Jupyter notebooks, just using one click integration between your GitHub and your Google Colab, you can run both of these Jupyter notebooks to your Google Colab account. So let's get started. Here at my public repo named public code, I have a folder machine learning. Inside machine learning folder, in this Keras heart disease live epochs folder, I do have these two Jupyter notebooks. And in this video, we are going to follow these two Jupyter notebooks one by one. We will start with this very first one. And in this Jupyter notebook, I am using a very popular and publicly available heart disease dataset. And it's a binary classification problem where using this data, we are predicting whether a person has heart disease or not. So this data set is very popular, everybody use it. And in this tutorial, our objective is to use the Keras based deep learning library to build a sequential network and perform the training with live metrics reading. I will copy this tab and I will go back to here, and here this is the another Jupyter notebook. I will open in another tab here. So now we have these two Jupyter notebook, And as you can see that these two Jupyter notebooks are directly connected with Google Colab. So I will be opening them in the Google Colab and I will be working at Google Colab environment. So let's start with the very first Jupyter notebook. So I am opening the very first Jupyter notebook, and as you can see that the Jupyter notebook is open in my Google Colab because I already have access to my Google Drive in the another tab. So the connection to Google Colab from my GitHub account was easily accessible. So let's start this code flow. So here, as we already talked about, that we already have the data set. As you could see, the location where this Jupyter notebook is running, it does not have access to hard data set. So what we need is to upload the data set from my local machine. So here we already have the code to upload the file. We will select this hard data set which is available on my local machine, and data set is pushed. Now we try to check again, and now we have the hard data set available. Now we can use and reference this data set wherever it's applicable. If you do not have this data set, you want to access it, the data set is also available at my public repo. If you go to public code and visit datasets, and you can see that hard data set is also available here. So if you want to access it, you can use this raw URL, and this raw URL will give you access to just download this data set using CURL or wget, or other option will be that you can just right click and save as. So whatever option is applicable for you, you can get this data set. Now we are importing the required packages which are needed for this demo. At the next step, we are reading this hard.csv, and here is our data frame. As you could see, that data frame is a collection of 303 rows and 14 columns, and the explanation of these columns are already defined here. Out of these 14 columns, the 13 columns are the columns which will be used to train our machine learning model, and the 14th column here is the binary column which shows whether, based on the values in these columns for a particular row, whether the person has heart disease or not. So here is the list of columns, and just to do some exploratory data analysis, we are going to look into the heart disease. Out of 303 records, how many records have heart disease versus how many record does not have. So as you could see that the distribution between heart disease being positive and negative, it's quite good. It means it's a very balanced data set. If we have the target values which are sway either one direction or another, then definitely it is not a good situation for us to perform the machine learning. So we made sure that we do have a really balanced data set. Next, just to see a couple of more information related with our data set, here what we are trying to do is that we are trying to plot the heart disease by gender. And here, as you could see here, that we are creating this graph where you could see that depending on gender, so blue is for female, as you could see, that's the more versus yes. So here you could see being heart disease is higher in male but lower in female. And here you could see that the distribution is kind of in a way that no heart disease, and this is quite balanced. If you would want to see the correlation among all these columns we have, all the numerical columns basically, to be very specific. Here you could see that the correlation, if you want to make this graph little bigger, you can change these RC params for the plot, and now you could see that this is how your relationship among columns is. So after that, we will go and we will start performing the earlier steps in our machine learning process. So this is our data frame, and now we need to split it into the target and the training data. So target is our very last column, which is the column name. So if we would want to see the column names, we can just put here df dot columns. So the target is our target column. So what we are trying to do is that we are taking this data frame and we are using from first all the way to the last -1. So from 0 to 13th, we are taking that input, creating the new data frame called df input, and we are splitting the data set. As you could see here, df input, it has 303 row and 13 column, and here is the df input sample look like. If you would want to see the sample row, you can just say dot sample and just give you 10 records. So now you are getting 10 sample records from this df input data frame. The code, let's put it here and keep this first df input as it is. Okay. Now for the target column, we are using the same command. The only difference here is that we are only taking the last column, and the column name is target. And as you could see here, the df target is just one column which includes all 303 rows. And if we want to see the values from the df target, these are the binary 0 and 1 values. So now we have got our training and target data set ready. At the next step, what we need to do is that we need to transform this training data so that it can be understood by the deep learning engine. So what this transformation does is that it removes the mean and scale the data to a unit variance. It means the data which we have seen like this way, as you could see, this numeric data which is human readable, and it gives a lot more sense to us just looking into that. We have to make it machine readable, and that's why we are using this sklearn pre-processing and using this method called standard scaler. And what this standard scaler method does is that it basically removes the mean and scale the data to the unit variance. So once we perform this transformation, and if you see here that we are using a standard scaler, and then we are processing this fit transform, and our input is our df input. So our input data frame is df input, and the result is df scaled input, and that's what you are going to see here. So this is the result, df scaled input. And as you could see here, that the same row what we have seen, so this row is transformed into this format. So all 303 rows, each row is transformed in this format. So this is our input data frame. Now what we need is that we need to split this data set into two sets. We need for training and for the testing. And to perform that split, we are using the scikit library, which has a method called train test split. And in this method, what you really need is that you can provide your input data, you can provide your target data, and you can provide what kind of split you want. Means your percentage, and rest will be taken care by the method itself. So as you could see here, that we have used this 30% split to create the df input train, df input test, and df target train, and df target test. And that's what it really look like. So you could see here that out of 303 records, 91 records are related with test, and 212 means 70% records are related with train. That's the reason of this 30% split. If you say I would want this 20% split and you run it, now you see that it became 61. So rather than that, depending on what your requirements are, you have your choice to do it. And I will just use a 20% now. So there you go. So our input data frame is split into training and test now. After that, now we are going to build the Keras classifier to predict the heart disease. So we are going to use these Keras models and Keras layers, and we are going to import the sequential and the dense layers. So our network will be type of sequential, and the layers we are going to have, they all will be the dense layers in this network. And here is the definition for our network is this. So if you could see here, model is type of sequential, and in this model we are adding these 3 layers, and 3 layers, they are fully connected dense layers, and out of them 2 are hidden and 1 is output layer. So very first layer, as you could see here, is a dense layer, and it has the 13 input, and that inputs the resemblance or match with all our 13 columns. And the activation method or activation function for this layer is the 10h. In the second layer is the activation is 10h, okay, and it has 20 neurons, and it uses the activation function as 10h. And finally, the third layer is also the dense layer, which has this single neuron, and it's using the sigmoid activation function, which is mostly selected for the binary classification problems. And if you remember, our binary target data is binary, which is the value of 0 and 1. So now our model is ready. We have defined our network for deep learning, and now we could start our machine learning process. But before we even start that machine learning process, we will have an opportunity to visualize our network. So here you could see that I am visualizing my network here. So here we are using the Keras utils and visutils, and we are importing this plot model, and then plot model, you just need to feed your model. This is the model definition. So model object, and it's going to use this, create this image file, and that image file will be visible here to show how our model looks like. So let's see here, and this is your model look like. And as you could see here, input layer is a 13, dense is input 13 to 13, and then it goes, okay, and then finally, so this is our layer 1 and this is our layer 2. And as you could see here, the definition. So the way this layer was created, this is how the system underneath, or the Keras engine underneath, understand your network and gives you its own understanding. So you could take a look and make sure it makes sense to you. In the next step, what we are trying to do is that we are doing something very creative here. What we are trying to do is that when we are going to start our machine learning training, we will try to visualize the real-time loss function or the loss value as the training progress at every epoch or every step. So now we are going to start. So now we will implement our loss visualization plotting function. So this code I have taken from this gist. So if you are interested to learn more about it, please click here and that will give you the access to this original code. So I'm just using it as it is. So the code, so we have to launch this. So import Keras, and now that code is accessible. And here, as you could see here, that we could start the compilation of our model, and here we can start the training. So I have moved this direction which was above to here because now it fits with our next step. So we are using this compile method, and that is using these three arguments. It's using the optimizer as Adam. So this is the algorithm. So this optimizer is basically an algorithm for the first order gradient based optimization. The loss is using the binary cross entropy. So it's basically the loss function which uses the logarithmic loss and which is really good for binary classification as defined in the Keras. And finally, the matrix we are using for this compilation is the accuracy matrix. And next we are basically starting the training. So that's the model.fit. We are giving our input data and target training data. So these two are the training data, and we are asking this training process to perform the 100 epochs. And at this point we are making this callback function to plot loss. So this function will call this plot loss function, which is going to provide the real-time training loss progress as we progress, and verbose means show the log to us. Let's run this process, and here you could see that epochs, and for every step the loss was started from here and it's going down and down and down. So for every epoch the loss is going down, which shows that okay, we are hitting almost 80, 100, and then all the 100 epochs are created. So this callback function was used to show this value. If we haven't used this function, for example, we take this code, just comment this code, do not use this callback here, and then if we run this code here, you will see that there is no need for this function. Your training is still working as it is, and all these 100 epochs are completed without any problem. So that's, I wanted you to show that you do have option to either see the callback function to see the live training and showing the how the loss function is really progressing, or if you do not want, you can just do not use this callback function. So I'm just making this callback function back to active, and we will go to the next step. And here all 100 epochs are completed. Okay, I do have another option for you. I do have another callback method, and which is called this plot learn loss with accuracy. So I have added this another method called plot learning, and that is what it does. It plots the loss with accuracy. So it's together. So it's like you are going to get loss with accuracy. So let's call this function. So this function is available, and now in the compilation which is already defined earlier, we are not changing anything. We are calling a different callback here, and that callback is going to show us the loss with accuracy. And here we are launching the training, and as you could see here that in this graph the loss is shown as every epoch, and here is also the accuracy, and almost all these 100 epochs are completed. So our training is done now. Now this is our model, and what I have done is that when this model training was done, I have stored the result from this process in this history object, which we will have opportunity to process little later. Sometimes you do not need to define it, you can just perform it as well. Next, model summary. Here we are evaluating our model. This is our input test data, and here is our target test data. So combining the results by applying the input test and the target test data will give you the accuracy for this model. And depending on these layers, the accuracy of our model is about 78%. If you are interested to know about history, so this is the callback history, and here are the keys in our history object. Here you can see loss and accuracy. So if you want to just plot the result between history and accuracy, that should give you that here is the loss and here is the accuracy. There is another option if you want to plot history and accuracy, and here you could see that using history and history accuracy, we are getting accuracy value, loss value, and we are plotting the accuracy and loss. So this method, which is already available for you to call history.history and plot, and then which take the keys and just plot it. So you have also got two different ways to see your results. And here you could see that each line and then the color is defined and then labels are accuracy and loss. Now if we want to create the confusion matrix for our result data set, so here you see this is our target and this is the test, and here we are using this model.predict by passing this input test. So this shows this is our confusion matrix for the given test data set. Finally, if you want to get the accuracy of your model, and here you could get that what's your accuracy. So this was a quick example to use the Keras sequential model and the dense layers to create a very small deep learning experiment to create a model to predict whether a person is going to have the heart disease or not. In this experiment training, we haven't used the validation data set. So I do have another Jupyter notebook, and thus I wanted to show you that in this Jupyter notebook, validation built into. So I will be opening it. And now the heart disease with validation Jupyter notebook is open directly in Google Colab. I would say that about 80% of this Jupyter notebook is identical with the previous one, the one which we have just used here. The only difference here is that when we are creating the training data set, we are also splitting this data set into the training and validation. So what I will do, I will walk this thing a little faster. Let's run. So first I'm checking the hearts data set is not available where this Jupyter notebook is running, because these two Jupyter notebooks are running in two different Python environment, and for that reason the heart data set which we have uploaded here is not accessible to here. There is where you could connect the runtime environment, but we won't be connecting here. We will be launching this line so we could upload our heart data set. After that, the heart data set is available here, and importing the pandas and the visualization packages Seaborn and matplotlib, we are importing the data set heart, and here is our data frame, which is same 303 rows and 14 columns. And first we are just doing visualization. We already have followed it, so I'm going to be going through it. And now as you could see here that this is our DF input and DF target, and at the next step we are transforming our input data set, and now it's DF scaled input, and now we are splitting the training and test, and here is our data frame, and as you could see it's a 212 rows means 70%, 70-30 split, so I will make it 20%. And now what we will do is that we are adding this validation data with the training. So that's the difference in this Jupyter notebook, which is not available in this one. And here we are using this 20% split, where 20% will be given to test and 80% will be given to training. And we are creating this X train, Y train, and X wall validation and Y validation. So here you could see that 193 rows and 49 rows will be used for validation. Again, our model definitions are same, and here is the model we have created using these three different layers. Everything so far is same. We are just visualizing our network, and next step, as you could see here, we are defining the loss plotter, and plot loss will be used here. And one big difference is here, as you could see that in the previous step when we were not using the validation data, as you could see here, the model fit, there was no reference to validation. However, in this example, we are using the validation data and we are passing our X wall and Y wall. So the training and then target validation data. So this validation data will be used when this model will be trained, and that's the reason when this training will be happening, you will see that graph for the loss and validation loss both will be visible. However, in this example, we have seen that only loss was visible, but the validation loss was not visible. So now we have this and we will try to run it. As you could see here, as epochs are growing and our training loss and validation loss is happening. And that's what I really wanted you to see. So that's a big difference between these two experiments. All the 100 epochs are done. We have already saw that this code, what it does is actually do exactly the same. Here we also have the validation data. So we will not run, we will just pass it. Now we can look into our model accuracy, and here you could see it's about 89% history. And now, as you could see here, it has the loss key accuracy and validation loss and validation accuracy. Versus if you look into the previous one here, we only had loss and accuracy. So validation added into the training, now we have those metrics as well. And here is the plot which shows both loss accuracy with the validation loss and the validation accuracy. And here is a way if you would want to make your plot by yourself. So this is already available. Here you could make your own. And now we are just creating this confusion matrix by using this input test data and target test data. Finally, model accuracy. If you want to check this model accuracy, here you could see that model accuracy is about 87%. So very quickly, we have seen in two separate Jupyter notebook that how you can create a Keras based experiment where you can add training data with validation or training without validation, and while the training is done, you can see the live experiment results with regard to your loss and your accuracy. After we have completed this work, if you want to save this data to GitHub, I already have the one-click GitHub save function enabled. I will say save a copy, and it already knows where this Jupyter notebook was saved earlier, and it will be updated there. And update is completed here. Close it. I will close this notebook. Second notebook, same thing, update it, same path where it's supposed to be, and the public code. So here it should be public code and the path, everything is correct. So these two are updated. I will close it, close it, close it, close it, and that's where the Jupyter notebooks are in my Google Drive. So these two Jupyter notebooks are already available at my public repo. So if you would want to give them, please clone them and run in your own Google Colab environment and enjoy it. So that's all I had in this video for you. and I will be seeing you in my next video.
That's all, my friends. If you have enjoyed our content, please like it, share it, subscribe it. And finally, please remember, be good and do good. Thank you.